well, thanks for the organizers for asking me to give this talk. Yeah, so as you see, I'll give a more old-fashioned whiteboard talk. So I'll talk about quantum collapse and awareness. So the older part of this work is joined with Andre Ranchin, and currently I'm discussing more things with Johannes Kleiner. Well, so I'll start by, well, just writing some big open problems. At least I think that they're big open problems in science. So so the first one, which I think is still a very big open problem, even though most physicists sort of might not agree, or, well, it depends who you ask, is the measurement problem. So this is in quantum theory. So I'll discuss much more of it later, but well, the idea here is, as you know, like in, let's say, standard, I mean, even without any interpretation or just in terms of operational quantum theory or mechanics, usually the way you learn it or the way you do experiments, there are two parts to quantum theory. I mean, there is sort of like some kind of unitary, you might say, deterministic part to it. And then there is another part which is called observation or measurement. Which again, I don't think it's such a big problem that when measurement happens that you have a different, well, something sort of collapses or you project something, that's fine. I mean, it's well-defined mathematically. What's not well-defined mathematically is what do you mean by a measurement? I think that's, to me, seems to be the big open problem. There is no definition of what a measurement is. And even though, again, from an operational perspective, I think most physicists, when you deal with some microsystems, they would know what does it mean to do a measurement, or now people working on quantum computers. I mean, a lot of quantum algorithms, well, use measurement as part of that's how you sort of get the result, and you know what does it mean to measure your quantum system. So in examples, people know what it means, but it's not clear exactly what this notion is. So I think, so the way I would view the open problem, the measurement problem, is really just understanding what measurement is, not, and later what it does. I think that's, of course, probably understand, I mean, it's essentially the same question from a pragmatic perspective. So I guess, so one question is sort of, like I said, so what is it? And sort of, well, what kind of effect does it have? So that's one big open problem. Now, the second big open problem that this conference is about, I guess, is, well, what sometimes people call the sort of the hard problem, or sort of what, of consciousness. So this comes from Chalmers, and but of course this is a very ancient problem of in how do you fit sort of subjective or mental phenomena in a physical world. Again, if you're an idealist, like we heard, I mean, maybe that's not a problem. Then you have the reverse problem: how do you fit the physical world in a mental sort of, but that's not, so let's take this as a hard problem. So the question is sort of how to understand subjectivity or subjective phenomena. And how does it fit subjective phenomena and sort of current physics? Right, so do we need to extend physics, or is physics already fine, or is there sort of, what kind of emergence is there, if it is an emergence? These are all the type of questions that arise when you look at this question. Now, I want to say some things about subjective phenomena. So I think if you think about the talks we had in this conference, so I mean, this was already remarked before, but so of course the word consciousness was used, right? But even here, I mean, when people were trying to model what this is, you see that they were modeling lots of different things. So, I mean, some of the talks were about somehow some kind of sort of conceptual, I would call it, or maybe information theoretic sort of content of consciousness. So this was some ideas about that. Well, our consciousness. I mean, it might be about relations and how different. If we look at some scene or some colors, how they relate to each other. So I think, this was one aspect, and also like aspects of, in what sense when we're doing mathematics, are we conscious, and what sense creativity or sort of, this was one part. I mean, and we also heard some discussion, for instance, like in Pete's talk, I mean, he talked a lot about feelings. And that was another aspect of this phenomena. And then there was maybe and there is clearly some kind of something we want to talk about, which is awareness, which also appeared in some talks. And this is very relevant to sleep and anesthesia and other sort of, and the list can go on. So if you analyze even just in the couple of days we had in the talks, when people were talking about consciousness, they didn't talk about the same thing, which is actually good. So I would claim that sort of consciousness is a very complex phenomena that has sort of many layers, and in some sense, I think it's a bit just misleading to just call it consciousness. So of course, this comes there are sort of the hard problem of consciousness and maybe easier problem of consciousness. And maybe part of them is sort of recognizing which parts of all these layers are difficult and which are easier. So if by easy you mean that, can sort of AI or some neural network can do some of these things and cannot do others, I think we'll be sort of maybe surprised in the near future by what AIs can do. I would actually bet that we will have sort of neural networks doing maths better than us, but we might disagree on that. But I mean, probably we won't understand what they do. I mean, they just write sort of huge proofs that will be verified in a computer, and we won't be able to understand the proofs because they'll be too big. But they'll still prove the Riemann hypothesis without us knowing how. They might be sort of creative. I think lots of things that we think are very human or very sort of special for consciousness maybe are not really what's important about this phenomena. I mean, they're very important, but not the hard problem. Maybe it's not there. But I would say that a lot of this comes from the fact that I think we have a huge lack of data. So it's a bit like if you think like some stupid examples. I mean, of course, we all live in the physical world, or so it seems at least. Now, because someone sort of lives in the physical world, sort of and has some acquaintance with physical object, he's not or she's not a physicist, right? I mean, to be a physicist, besides sort of learning a lot, I mean, just the science of physics required a very long evolution of study of very precise behavior of physical phenomena. Well, the same thing with medicine. I mean, for a long time, people thought had some ideas because, of course, everyone has a body, and we're all sort of sometimes we're ill and sometimes we're healthy. So, well, but we're not all doctors because of that. So, and I think if you think about sort of what's going on sort of now with the science of consciousness, so it's true that in some sense the behavioral revolution in the beginning of the 20th century sort of came because of that. I mean, I think what you have to say, and this is sort of similar, like, let's say, to Aristotelian physics or sort of more ancient forms of medicine, we already have some sort of theory of consciousness, which is very cultural. It has to do with sort of our languages and our culture, so what we think we do with our minds and lots of sort of cultural history, what our philosophers told us, and there are lots of different ideas, but it's based on very little observation. So, I mean, so of course the behaviorists said, yeah, I mean, I think that's a problem. So how do we make this into a science without just letting people say what they think it is? Well, we'll just examine very specific kind of phenomena, well, like a third-person phenomena. But that's, you know, it's not a good analogy, but that's a bit like sort of medicine evolving by just saying we'll just study skin sort of conditions, and that will solve everything. So I think that's a huge problem, I think, in this area, which sort of explains why there are so many different ideas what consciousness is. So I'll just give maybe just some examples of what's missing. I mean, you already here see that there's some kind of a layered structure to it. And perhaps this is actually what does happen. So maybe I'll say I welcome all of you to start meditating. I think that's, if really we want to become sort of serious, again, you don't all have to do it, but at least when you work on consciousness, you have to work with people who supply the actual data. So really do very careful observations of experience. And I think that's a much better way of describing. So instead of consciousness, maybe we should really talk about experience. And let's say subjective experience. And we need to start really analyzing it very carefully. Because I think there are lots of misconceptions that come from cultural and linguistic reasons of what experience really is. So, you know, one example that sort of tries to connect these things, I mean, in IIT and theories of sort of information, I mean, if you look at the axioms, I mean, it seems like sort of consciousness or experience, I mean, there couldn't be a subjective experience that doesn't have content. I mean, it seems at least that it's very unclear if that sort of fits with the axioms. And I would claim that there is, I think there is such a thing, and I've observed it, and I think we all can. So, for instance, I would claim that there is sort of contentless awareness. So, which doesn't really fit many of the paradigms we heard in this talk. And I would even claim that this is much more prevalent than we think. So this happens, so I've heard reports of that. I haven't experienced this myself, but I think it's worth trying. I mean, it's just very difficult. That even in sort of like if you're in dreamless sleep, or in very sort of in states of what many people will call unconscious currently, you still have this contentless awareness. So that's one thing that is worth sort of experimenting with, checking. I mean, getting reports for as many people as we can. Is that possible? There is such a thing in awareness or experience, subjective. I mean, another thing is, I think, you know, Wittgenstein talked a lot about sort of this aspect seeing. And he sort of looked at very simple examples that sort of came from Gestalt psychology, where you have sort of an image that you cannot decide I don't remember, if it's an old lady or a duck or sort of other kinds of things like that. But again, maybe this is much more prevalent than we think, in the sense that if we, well, now I'm giving some kind of proto-theory of sort of the development of sort of experience. I mean, in a not evolutionary, but from a developmental perspective, I would say that sort of babies, for instance, they still have experience, but it's much more sort of, almost everything is like this aspect seeing. I mean, things sort of shift around all the time. The basic nature of our experience is not as we think, or as IIT, for instance, tries to say, has some sort of content, which is, we can see this is red, this is, the scenes we see, there's a clock over there, there's a person over there. All of these things are things that we develop as from, it's something one can observe. I think one can observe if you try to sort of be, so this is this contentless awareness. You can also ask about some kind of like, what is prelinguistic or awareness. And I think you can easily find that sort of when you relax and sort of learn a bit how to do it, even like scenes that you see, I mean, like the visual, they start shifting. I mean, there's no clear boundaries, and there's no sort of, so this aspect seeing of things changing all the time from one to another, and you have to make a choice, and you think you make it, but then it changes. This actually happens to us all the time. We're just, in many ways, it happens in a way that it's not that we're completely unaware of it. We try to ignore it as much as possible, probably because it's not so good. When you walk around the room, you don't want to bump into things. So you don't want the table to turn into something part of the scenery. You want to sort of have an obvious object there to avoid. But still, it does happen in experience. So there are lots of interesting things about our subjective experience that we're completely ignoring, I think. And many of the talks and models are in some sense ignoring, I would say. I'm not saying that these, we have models, if you do look at sort of what more like conceptual kind of experience, or more like linguistic awareness, I mean, sort of this is where we shape our experience according to some sort of intersubjective community standards, and this sort of helps us as a community and in our lives. I mean, then maybe some theories are good for that, and maybe other theories are good for for feelings, like what we heard in Pete's talk about how we feel things and how the structure of that might be another model. And the thing is that there might be lots of models, and we need to then in the end fit them all together. But and by the way, another thing which is being ignored very much and it's very much, I think, relevant for feelings is the body. We just try to think about consciousness as somewhere just in the brain, or awareness, but awareness is not just in the brain. I mean, it's a bodily thing, and maybe a lot of our feelings are really gut feelings in a very actual sense, and feelings, by the way, I would also include here. Maybe even Hume would agree with me, is sort of understanding. I think often understanding is really a feeling. It's not some conceptual, you get good at something and then you feel at ease and then you say that I understand it. And before you feel at ease bodily, you feel like you don't understand it. So we need to be really careful. I mean, that's not really what my talk is about, but I think it's very important to start really looking very carefully at our subjective experience when we develop all these theories. So, and actually in some sense, what my talk will be about is what I think is sort of the ground of where everything is built on, and this is this kind of contentless awareness. I think some kind of a theory of our subjective experience will start with some kind of a ground, which will be contentless awareness, and other things will build on that, in addition to our body and sort of feelings that are so. But I don't have such a theory, but I think that's a place to go to. And of course, there's another problem that, I mean, which is quantum gravity. So that I won't talk about at all. But you see, it might, well, it might, of course, relate it to quantum. So the first problem is related to that. So in terms of solutions, so possible solutions, so one solution is, and I think this term, again, I read it in Chalmers, but I'm not sure it is some kind of an illusionism, which people apply to sort of, well, again, let's forget about quantum gravity. I don't think people apply to that. But definitely to the problem, the measurement problem and the hard problem of consciousness, you'll have lots of people who will just say that these problems don't exist. That sort of, in some sense, all my talk about subjective experience and so on is an illusion. It's just a completely, just a verbal thing. You know, in our community, we talk about things, but it doesn't. It's just all illusions. And of course, there are and I think many of us here disagree with that about this problem. But I'm not sure about the first problem. I mean, I think the majority of physicists will actually say that in some sense the measurement problem is an illusion. And there are lots of, and there it's a much more precise statement in the sense that there are lots of possible theories. I think we'll hear one after my talk about why a sort of collapse or measurement, well, maybe measurement happens in some sense, but collapse never happens, or at least not in the ways we think it happens. And again, there's a long debate about can you be an illusionist about measurements. I'm not convinced, but I'm not saying that that it's not possible. So my basic assumption in this talk, the basic assumption is that that these are actual problems. So we're not deluded about the hard problem or about our subjective experience, and we're not deluded that measurement happens or collapse happens and we need to explain it. And you might disagree with, but for this talk, let's just take this as a basic assumption and try to see what we can do. So the question is now, can we come up with, well, how do we solve these problems? So of course, like a good question is, can we solve them together? So this is like an optimist approach. Maybe we can just, I mean, maybe not, but we can try. So what do I mean by that? So I think if you take seriously the hard problem of consciousness, like we heard in many of the talks, for instance, like yesterday evening, it seems like you might need to modify current physics. Maybe not necessarily, but it's a possibility. So the question is, can we modify current physics in the minimal way that would also help us solve so we're looking somehow for a minimal extension of the theories we know that will solve both these problems. So that's, we're looking for sort of a minimal extension of physics. I mean, of course, you might say that you need a completely different theory of that everything we're doing in physics is completely wrong, but that would be a very difficult program to do, right? I mean, we like, the physics we do, we like quantum physics. Let's just try to, if we can just find a minimal modification that would do it. So we do already know about the minimal modification of physics that does solve the measurement problem. And these are what I'll talk about later. These are the collapse models. Of quantum theory. And I think what, so I'm a mathematician, not a physicist, and really what I like about collapse models is that they have a very beautiful mathematical structure, in the sense that, it's for as a mathematician, it's nice to see that there's really a structural way of doing it. You might think that there is just one collapse, or like 5 people came up, each one with a collapse theory, but no, there's like a general mathematical structure of how to produce collapse theories. So there are infinitely many collapse theories, and you sort of can choose the collapse terms, and I'll try to say some things about that. But there is a sort of a well-developed mathematical general theory about what collapse theory is. So, I mean, we heard from Roger about one, but there are many others, and they all sort of share sort of the same mathematical structure. So that's already a good thing. And I would say about that, so in terms of the illusionist perspective, so all the illusionist perspective, I mean, the models they propose, which are very interesting, even though sometimes I don't understand them or disagree with them, I mean, they don't differ at all from from sort of standard quantum mechanics. So, but these collapse models do, which is a good thing. So and I think it's really interesting that now currently people are doing more and more experiments about collapse, right? So instead of just looking at microscopic quantum systems, you're starting to look at bigger and bigger quantum systems. So I think one of the basic questions is how big a quantum system can you put in superposition? Now, according to quantum mechanics, of course, there's the problem of decoherence. I mean, there's the environment, which is, but that's in some sense a practical problem. It's not, in principle, if you isolate any system enough, you can put it in superposition. Everything is quantum. Not in practice, maybe, but so what people are doing is they're starting to look at bigger and bigger quantum systems and seeing, and if you think about that, something like from like one nucleon to sort of is completely quantum, and 10 to the 18 nuclei is something like classical, some dust or something like that. I think people are now like at 10 to the 5 or something like that in terms of how big they can put things in superposition. And I predict that in the same way that sort of physics completely changed around the beginning of the 20th century, because people did experiments and things just didn't work out as they expected with black body radiation and things like that. Similar things might, and I think will happen, but of course, not everyone will agree with me, with quantum physics. I think that when we try getting bigger and bigger systems, we might observe, even though we might manage to sort of isolate them very well, they will collapse faster than we expect them to collapse. In terms of sort of the coherence time and things like that. I think that's an actual possibility. And already experiments are made that sort of, we can talk about this later, that indicate that maybe something strange is happening. So there actually might be an actual sort of experimental reason to adopt this theory. So now, how does this tie to the second problem? So what I'll do, I'll sort of show you some kind of sort of a toy model. So here we'll use the fact that this is the nice thing about collapse models, that you can, the collapse term is really up to you. Well, again, I'm not going into sort of free will and what do I mean by up to me, but just mathematically there's infinitely many collapse terms I can plug into the theory. And one possible model for this is sort of like you can define some collapse which is caused by something you can call quantum integrated information. Or at least, again, also what you call integrated information maybe is up to you. There are infinitely many theories that do that, and this is one version of some quantum integrated information. So when I say collapse caused by this, what I mean is that, well, you see there'll be some sort of nonlinear Schrödinger equation, and the nonlinear term will have to do with some kind of a measure of a quantum integrated information. Now, this is this joint work with Ranchin. Now, I'm not saying that this is sort of a good model of what's going on, but I think it's in what it does indicate is that one can relate sort of the collapse term again. So I think it's very important to understand that this is not, there are lots of old versions of consciousness causes collapse, or awareness causes collapse. And this is more subtle than that. It's not that there is somehow that when some conscious agent observes something, again, because then it just, begs the question. I mean, it's undefined. We don't know what consciousness is or what awareness is. So, we just, instead of saying measurement, now we say consciousness, but we didn't solve any problem. We don't know what we mean by this. So this is a very, precise mathematical theory that sort of you have a quantum system, you measure something about this quantum system, you call it quantum integrated information because it's similar to things that Tononi has defined. Now, I don't know if this has anything to do with awareness or anything, but it's some property of a quantum system, and you plug it into the Schrödinger equation, and this sort of, again, it doesn't cause, so collapse doesn't happen. It sort of helps the collapse happen. That's sort of the way it works. So it's, and that's just a general feature of these collapse models. It's not that there is sort of like a projection, a precise projection into one of the eigenvectors caused by something like this. It's just that the higher this term is, it's more likely sort of to converge to some state. That's how these things look like. So again, I don't think that this is the correct theory. And one of the big problems, well, it has lots of problems. One of them is that it's very non-local. I mean, much more non-local than you usually expect in physics. But maybe that's, I think the problem for me is that it's very ad hoc. And that's in some sense maybe a big problem in general, I think, with integrated information. I mean, it's a beautiful theory, I think, and it's great that it sort of somehow brought back the idea that you can measure sort of consciousness or awareness, because, of course, for us, if you're a naturalist, something exists if you can measure it. So I think really the great power of Tononi, or the genius I see in it, is that it completely reversed this sort of behaviorist sort of revolution. Because if you try to measure things, and if it is possible to measure things, this means that consciousness can be part of physics or part of nature. And for many years, you were not allowed to even say it. So this is what's so great about Tononi's work, even though maybe it needs to be modified, or maybe it only discusses just some part of experience and not all of experience. There are lots of things to talk about that. But the problem is that it's not clear why this measure or not other measures and so on. So I think what this opens up is to the following thing. It's it opens up, and this sort of then goes to the work of Roger and Stewart, sort of the possibility of a close connection between collapse, I would say collapse terms, actually, not the collapse itself. So the collapse part of the nonlinear Schrödinger equation, and I would just call it awareness. In the sense that this toy model at least shows that it's possible, right? That you can have a collapse term that somehow has something to do with awareness, perhaps. And this, so I think the bold step, and I think this is the one taken by Roger and Stewart, but I actually agree that this is a really good way forward, is just to take this as a definition. So I would sort of, and this would give us sort of a precise, okay, I'll say more about this, but I'll say sort of that the collapse, again, term, because the thing is that in these theories, like I said, collapse doesn't just happen. I mean, there's a tendency, the equations sort of lead you into certain sort of wave functions, and there's still an interesting way how to interpret this as collapse, actually. But the collapse term is some kind of proto-awareness, or what here I called this contentless awareness, which of course might then say that proto-awareness is much more, exists much more than we think in nature. But But I think what's good about this, if you look, go back to the step 1 of this kind of research program, so this is an empirical problem. I mean, in the classical sense of physics, right? So finding which collapse model, so like collapse theory, or so this is an empirical problem. What do I mean by that? So, like I said, we will do more and more experiments about, well, so as usual in science, we'll build sort of models, and then we'll try to sort of do experiments to check if they're correct or not, or falsify them or not. And by doing this, we'll find out things about how the collapse term needs to look like. And this will just come out of just standard physics. So it wouldn't be ad hoc like in this second sort of toy model where we just say, well, collapse needs to happen because of this, or it could happen because of gravity, or it could happen because of mass, or it could happen, I mean, there are lots of possibilities of, and like I said, the mathematical structure allows you to give infinitely many collapse theories, and which one is the correct one will be determined, well, first one, it might be that there's no collapse term, even though, like I said, I don't think this will happen. But this is so all of this is based on this sort of empirical question. So we'll study collapse more and more, and we'll find out exactly how we need to modify physics. But then we will make this sort of definition. So this actually will give us a definition of what do we mean by proto-awareness. A definition that is not, again, now, of course, the question would be then we will do all of this phenomenological study of our awareness and so on, will be have a very clear view of what do we mean by that. And then it will be very interesting to find out if this actually is a good definition. In the sense, does it, so we'll have a lot of data by sort of introspection, so which we'll discuss with each other, and also, intersubjectively we'll agree that, yes, we have these experience of contentless awareness, and it behaves in certain ways. It might be very difficult to explain it in words, but still we can try and do something. And then we'll see if what physics sort of says that how collapse behaves has anything to do with that. So that's, and if it does, this will say that this is a good theory. So now, and after, so this means that from my perspective, like a lot of what we can do now is actually just wait and see if we really want to see what happens with these collapse theories. We still need to do many more experiments. But what we can do as mathematicians in terms of modeling is if we do assume collapse models, and if we do take this definition seriously, we can then, and of course, sort of Roger and Stuart have been doing this for many years. I'm just saying that there's a sort of a more general sort of background where you can play with this. I mean, you can look how sort of these kinds of mathematical theories, how sort of you can have emergence of, if this is like the ground, this contentless awareness, how can other things like feelings and conceptual information and so on, all these other theories, how do they emerge for a given, for the human body and brain, or from other animals, how do these things emerge from this kind of contentless awareness? And we might find out that actually, in some sense, what's happening is that we can explain many of these things without really, in a much more classical sense. I mean, that this is sort of what gives flavor to everything. I mean, without this, we might still be able to do a lot of these other things, but be zombies. Now, again, in terms of the philosophical zombie or so on, I mean, I would just say that if what I'm saying is correct, then in our world, there are no zombies because, contentless awareness or proto-awareness is everywhere. So such a notion cannot happen. But in principle, in some other universe, maybe you can come up with a physics that, that there's no collapse, for instance, and then such things can happen. So a different physics might allow it if you take this as your definition. Okay, I don't have a long time. This took longer than I expected. So I'll just say a few words about sort of the actual mathematical models behind this. So what is the structure of quantum collapse theories? I mean, there are different ways of approaching this, but I think one way which is very nice is this kind of these Lindblad equations, which are very, in some sense, they're sort of almost obvious if you have the right idea. And so what you want to start is, well, you know, in quantum theory we describe, so from the Heisenberg perspective, we describe things in terms of observables. And observables, they need to form some kind of an algebraic or topological algebraic structure, which could be a C-star algebra or a W-star or von Neumann algebra. So you start with some kind of, you know, so A is some kind of von Neumann or W-star algebra, right? Now, if you're doing sort of, you know, quantum computing, like finite quantum systems, you can think of just matrices, n by n matrices, but you can apply this to, you know, to sort of bounded operators on a Hilbert space and many more. So this is a very general structure that sort of describes observables of a quantum theory. And now what you want to define is sort of like a time evolution of such a system. Now, and in usual quantum mechanics, the time evolution is a unitary time evolution. So you want some mathematical definition of an evolution which is not unitary, but still satisfies good enough properties. So you call this thing a dynamical semigroup. So what is it? Well, it's a one-parameter family. Let's say phi t of maps from A to A, sort of linear maps from A to A. And here, so t is just bigger than 0. So we're not saying that you can, so you can go into the future, but you can, this is not reversible. And this originally was developed to discuss sort of open quantum systems. So if you have a quantum system in a heat bath, how does it interact with the heat bath? So you're, and you just assume things about, well, sort of natural things. So you want phi t, sort of these maps should be positive maps. So in any such star algebra, you can define positive elements. So a positive element is an element of the form, you know, if you can, so B is something like A star times A. So it needs to preserve the sort of positive cone. You want it to preserve the identity. Now you want sort of this semigroup property. So if you, so this is something like this. So if you evolve in time sort of by s seconds and then by t seconds is the same thing as doing it by t plus s seconds. So this is being a sort of a semigroup. You also want some properties that somehow, if you look at phi t of x, this as t goes to 0, this does approach x. The limit is x, and in the, well, there are lots of topologies on some, I won't go into the details of what do I mean by this, but somehow like phi of 0, well, so this is a natural condition to ask. And then also you would ask that somehow phi t is sort of, is continuous or normal. What, I mean, again, it's not so important, but the point is that under these conditions, like in general, if you have a one-parameter family, you can ask, well, what's the derivative of this one-parameter family? So you can see that under sort of good assumptions, you can write phi of t is the exponential of some t times L in quite great generality. Again, I won't go into the entire theory. And then, you know, this somehow goes into some theory of sort of, you need to talk about completely positive maps and to have a good theory of this. So, well, just 5 minutes. And then what you can do is sort of study the structure of such an L. You know, what kind of an endomorphism of your von Neumann algebra does L need to be? So you can sort of define a notion of what I think Lindblad called a sort of completely dissipative element. So L from A to A, which satisfies sort of that it takes the identity to 0, it preserves the star operation. And you essentially want that if you look at something, it's not a derivation, but it's close to being a derivation. So you can look at sort of what L of, for any elements, x star y minus L x star y minus x star Ly. You want this to be positive for all x and y. Well, actually, you need this also for matrices over A, but let's not get into that. So this kind of condition, you see, if this equals 0, this is the condition of being a derivation. And then this would mean that since all derivations of von Neumann algebra are inner, then this would sort of be a unitary operator. This condition would imply that it's sort of like a self-adjoint thing. So that you're just exponentiating that. But in general, it doesn't have to be 0. It just needs to be positive. So this is what you would call this sort of a completely dissipative operator. And so these will be so there'll be a set of such things, of all the completely dissipative things acting on A. And actually, you can also give a nice structure theorem of how they look like. So again, under some assumptions, the structure theorem will tell you that these things, for lack of time, I won't say it, but they're nice, nice structure. But the thing is that we can sort of, there's, for interesting von Neumann algebra, this is an infinite set, and all of these things are actually good collapse terms from that perspective. So that's what I mean by a good collapse theory. And besides that, you can also then relate this to some kind of, quantum stochastic equations. So under very general conditions, this kind, so here the way we would think about this is that this is how things act on the density matrix. And you can ask, is there some action on the actual vector in the Hilbert space? Is there some that are related to this, these master equations, as they're often called? So is there a quantum stochastic process that sort of gives you, when you look in expectation, would sort of give you these kinds of processes? And there are. So there's, again, a nice dictionary between some kind of stochastic differential equation and Hilbert spaces, which are exactly, these kinds of nonlinear Schrödinger equations and these general things. But you see that from a mathematical perspective, it's a very nice theory. And you have sort of infinitely many possible collapse theories. And again, what's interesting about this that I don't have time to say is that you also see that mathematically, this you can always write such a completely dissipative thing as something which is self-adjoint plus something sort of dissipative. But this writing, so like the self-adjoint part gives you like the Hamiltonian is the physics or the standard physics, and then you have the collapse term. But writing it in this way is not unique. You can write the same thing in many different ways, which tells you that, I think that's something that physicists didn't look into very much, that from this perspective, if you look at it abstractly, you can get, for the same collapse theory, there are different sort of quantum physics corresponding to it. I mean, there are different Hamiltonians that would give you the same physics, but, the same collapse physics, but original quantum theory would be different. I think that's an interesting thing to look at. So I'll just finish. Well, I think my time finished, but I'll just give you like 2 more minutes of some examples. So like the basic thing, the sort of GRW example, it sort of looks essentially like this. You have your density matrix, and you're putting a differential equation on how this changes. So the first part is just the usual Schrödinger part. So you have some Hamiltonian. But then you want to add to it, or subtract some operator of this thing. And what does this do? This somehow suppresses the off-diagonal elements. So if I look, and again, there are lots of different choices of what you can do, but one way of saying it is that if I look at the matrix elements of in the positions of the basis of this, well, they are like the matrix elements of the original, but somehow I want to multiply them by, so here I'll put some constant, this GRW constant, and times sort of 1 minus e to the minus x minus 1 square, and again some other constant square. So in other words, you see that what happens, well, you can analyze this, and sort of this will tend to sort of take your, to make this into sort of like a class, I mean, a combination of pure states in position space. So all the off-diagonal things will get sort of disappear with time. And this is the nature of this thing. And I think, so here you can already see how we can play with this. I mean, so it's clear what we want to do is we want some, this function, what it needs to do if we want it to sort of collapse, at least in the position basis, it needs to sort of take the off-diagonal elements and get rid of them somehow in some fashion like this. But this function is arbitrary. I mean, it's a nice choice for certain reasons, but you can choose other functions here. And these constants, for instance, are again, well, in some sense arbitrary. I'm not saying that they're not correct or anything like that, but from a mathematical perspective, you can put that these constants that somehow, so this is just for one particle, but you can do similar things for more particles, and then the number of particles or their masses will come into this picture. But instead of looking at sort of collapse things that measure the mass, and this is sort of how much collapse you have, you can measure other things about your system, and the higher it is, it will collapse more. I mean, this off-diagonal things will collapse more. And this is sort of what we did in this model. We defined this kind of phi of rho. So this was, again, you need, it works very well for finite quantum systems. Otherwise, you have to, so let's assume for now that it's finite. So you take the inf on some quantum relative entropy of S of rho relative to, well, you break up your system. So you trace out over these things where, sorry about this, where here what's going on is I'm writing over all the ways of writing my system as, well, as a bunch of systems. So I'm writing my Hilbert space as a tensor product, and for each such things I can sort of trace out my density matrix over this thing. Look what happens at each part somehow. And then I can, this is sort of like the quantum relative entropy, which again is defined in some trace of sigma log the other thing. So then I can write a model, well, at least in the finite setting, because you see, otherwise we'll have to have problems of, well, maybe I can write this as an infinite tensor product. And I can write a model where these kinds of constants depend on this quantity instead of mass. So this is a kind of this, the collapse terms have something to do with some kind of integrated information. In what sense the system is more than the sum of its parts. I'll just finish, so one last thing. It's really interesting to notice that in these collapse theories, all of these, well, there are collapse theories when you write down the stochastic quantum stochastic differential equations, they can be continuous. So you can have some of them, like these things called CSL, and there are lots of other variations. But what's going on is that collapse is caused, or the collapse term, is a space-filling classical stochastic field, which then interacts with the wave function. And if you think about it like that, in these models, if I do put this equation of, if I do think that somehow collapse term has something to do with proto-awareness, in these models, you have that proto-awareness is not just something that happens in, I don't remember how you called it, like blips or bings. Yeah, it's not just something that suddenly happens. I mean, you can have models like that, but you can have a model where the collapse term is there constantly, and it actually fills the entire sort of space. So it gives you a completely different way of thinking about sort of proto-awareness. So that's another possibility. And if, for instance, experiments would show us that these theories are better ones, we might need to rethink about what proto-awareness is, if, at least according to this line of thought. Thank you.